Jane, whose mass is 50 kilograms, needs to swing across a river having width d, filled with person-eating crocodiles, to save Tarzan from danger. She must swing into a wind exerting constant horizontal force F on a vine having length L. So here is the wind, and this has length L, and initially making an angle theta with the vertical. Take D as 50 meters, F 110 newtons, L 40 meters, and theta 50 degrees. With what minimum speed must Jane begin her swing to just make it to the other side? Once the rescue is complete, Tarzan and Jane must swing back across the river. With what minimum speed must they begin their swing if we assume that Tarzan has a mass of 80 kilograms? Okay. Now, we can see this situation here. Here is Jane at a height h with respect to Tarzan. This is delta h according to the figure. This is L, length of the string, so we're going on the circular arc in order to save Tarzan. The initial angle with the vertical is theta, so this distance is L sine theta, this distance is L cosine theta. And if we have an angle phi between for the other side, then we have L sine phi as this distance, L cosine phi as this distance. L sine phi plus L sine theta will add up to the distance between Jane and Tarzan on the x-axis, which is d. So let's start with noting this fact. L sine phi plus L sine theta must be equal to d, the distance between the two edges. So we're going to take L as 40 meters, theta as 50 degrees. So that means we have 40 sine 50 plus 40 sine phi, which we don't know. This must be equal to d, and d is 50 meters. So this is going to be equal to 50. So we find that phi must be equal to sine inverse or arc sine 50 divided by 40, which is 5/4, minus sine 50 degrees. And you can see that this is 28.9 degrees. Now the perpendicular distance between Jane and Tarzan, that is what I call delta H here, can be calculated from this geometry as well. As you can see, this is basically L cosine phi minus L cosine theta. So this distance is L cosine phi minus L cosine theta. This is 40 times cosine phi, cosine 28.9 degrees, minus cosine 50 degrees. And we find that the perpendicular distance between Jane and Tarzan is 9.31 meters. Now what I want to do is to, so this is part A of the problem, I want to draw a free body diagram for Jane, and I'm going to do this during the swing, because when Jane is on the other side, there is a normal force, contact force with the ground, but as soon as she starts the swing, this force will disappear, obviously. So let's call this is y-axis, this is x-axis, horizontal axis x, vertical axis y, and here is Jane. Jane feels the weight, mass of Jane times g, the gravitational acceleration. There is a constant horizontal force F, that's the wind acting on Jane. So this is a constant force F in I hat direction, which is an external force on the system. And because Jane is swinging, there is a tension on this string, tension T, which is pointing towards the center of this circular arc. So you can see that Jane is going to move along this circular arc. Okay, so we can see that the total mechanical energy, which is kinetic energy plus potential energy for Jane, will change during the swing. Why? Because we have an external force acting on the system. Delta E mechanical is equal to W external. The external force F will change the mechanical energy. So what is the work done by this external force? The force is in I hat direction, causes a displacement in minus d I hat. So this is basically minus F d. So we can see that the change in kinetic energy, delta K, plus the change in potential energy should be equal to minus F d. So the final kinetic energy minus the initial kinetic energy plus the final potential energy minus the initial potential energy is equal to minus F d. And the final kinetic energy will be zero because Jane will swing and will just basically capture Tarzan and stop. And then at that point they will start swinging back. So this is going to be the final kinetic energy. Initial kinetic energy is 1/2 mass of Jane v square, v initial square, plus the final potential energy. If I call the final potential energy as 0, there is an initial potential energy which is mass of Jane g times delta H, because I'm at a height h. So this must be equal to minus Fd. So I find that 1/2 mass of Jane v initial square is Fd, if I take Fd to the left hand side, minus mass of Jane g delta H. And from this I can isolate the initial speed. V initial is 2 over mass of Jane, parentheses, Fd minus mass of Jane g delta H, which is numerically 2 over 50, 110 newtons, 50 meters distance, minus 50 kilograms, 9.8 meters per second square, 9.31 meters is my delta H, and then I find this initial speed to be 6.13 meters per second. Now you might be wondering why I didn't consider the work done by tension. Now you can see that tension is a central force, and my displacement vector here, dr, so if I have a displacement vector dr, this is perpendicular to tension. As you know, the work done by a force that is perpendicular to the path taken is always 0. So there is no contribution to the work by tension. So note that tension is a central force. It points towards the center, and we're performing a circular motion on the arc of a circle. Therefore, the work done by tension is 0 and should not be considered as a contribution here. Okay, so this was part A of the problem. Now part B, once the rescue is complete, Tarzan and Jane must swing back with what minimum speed? So in part B, again we're going to have a change in the kinetic energy plus potential energy of the system due to the external work done, because there's still the wind blowing, and the total mass of Jane and Tarzan is 80 plus 50, which is 130 kilograms. So the final kinetic energy, so they will just make it to the other side and stop. So we're going to have a final kinetic energy of 0. Initial kinetic energy will be 1/2 m total v initial prime square plus they're going to gain potential energy m total g delta h. Initial potential energy is 0. This will be the work done by the external force, which is Fd. So we will find that the initial speed will be square root of 2 divided by m total g delta h minus Fd. So if we plug in the numbers here, this will be 2 divided by 130 kilograms, 130, 9.8, 9.31 meters minus 110 times 50, and this turns out to be 9.89 meters per second initial speed for Jane and Tarzan swinging back together. Okay, so to summarize, we have Jane and Tarzan on two sides of a river. There's a person eating crocodile in between, and Jane must save Tarzan. So to do that, she goes on this circular path connected with this string with length L to the to a pivot point on the tree, and they swing back together to the other side. There is always a wind blowing to the right, with a constant force F. So first we have considered the geometry. We found that the perpendicular distance between Jane and Tarzan must be L cosine phi minus L cosine theta, the blue minus the green, and the horizontal distance between Jane and Tarzan is L sine phi plus L sine theta, which is d. This allowed us to calculate phi and the distance, perpendicular distance between Jane and Tarzan. When I look at free body diagram for Jane during the swing, I see that there's a constant horizontal force F, which is an external force. There is the weight of Jane, and there is the tension on the string. And because I have an external force acting on the system, this is going to change the mechanical energy of the system. Kinetic energy plus potential energy will be changing due to the work done by this external force minus Fd. And since the tension is a central force, it's always perpendicular to the path that Jane is following. So the work done by tension is 0. Basically, this change in the mechanical energy is due to this external force F. And from that, I can calculate the initial speed of Jane, because final kinetic energy will be 0. And I consider potential energy to be 0 at the level of Tarzan and mg delta h at the level of Jane. So when they swing back, what changes? well, this external work done will be plus Ft I hat plus Ft if I hat dot d I hat, and there will be a change in the total mass, and the rest of the story is the same. We're going to reach a zero kinetic energy on the other side, and the potential energy will be increasing here instead of decreasing. Okay, let's move on to another example. A ball of mass 300 grams is connected by a strong string of length 80 centimeters to a pivot and held in place with the vertical string. A wind exerts a constant force F to the right on the ball as shown. The ball is released from rest. The wind makes it swing up to attain maximum height above its starting point before it swings down again. Find h as a function of f. Evaluate h for f equals 1 Newton and 10 newtons. How does h behave as f approaches 0, infinity, and also consider the equilibrium height of the ball with the wind blowing, determined as a function of f and evaluated for 10 newtons and infinite force f. Okay. Now, when this swings to a height h, we're going to make an angle theta with the vertical. So there will be L sine phi, the horizontal distance, and L cosine theta, the vertical distance, the projections of the length of the string on vertical and horizontal axes, so that h plus L cosine phi will be equal to the original length of the string. So this allows me to calculate h as h equals L minus L cosine theta, and the distance I travel on the x-axis is L sine theta. So I see that cosine theta must be equal to L minus h divided by L. So if I draw a right triangle here, and note that cosine of theta should be L minus h divided by L, then I find that the other side of this triangle will be L square minus L minus h square square root. So this allows me to write sine theta as square root L square minus L minus h square square root divided by L. Now there is an external force acting on the system F to the right, so that will cause a change in the mechanical energy of the system. W external is delta E mechanical, which is delta U plus delta K. The force is in I hat direction. The displacement is L sine theta in I hat direction. So I find this is FL sine theta. The change in kinetic energy of the system, if I am reaching the maximum height here, is final kinetic energy minus initial kinetic energy. 0 minus 0 equals 0, because I start from rest and basically the ball is released from rest, and I reach the maximum height, which means also the final kinetic energy will be 0. On the other hand, the change in the potential energy, U final minus U initial, will be mgh minus 0. So I take the reference potential energy to be 0 at the bottom. So with that, the change in the mechanical energy, mgh, will be equal to the work done by this force, FL sine theta. I substitute for sine theta, square root L square minus L minus h square divided by L. And you can see that L's will cancel here. And if I take the square of both sides, I will have mg square h square equals f square L square minus L minus H square in square brackets. So this is going to be F square. If I open up L minus H square parentheses, I will have L square minus 2LH plus H square. And this is going to be, if I operate the minus sign, L square minus L square plus 2LH minus H square. L squares will cancel. So I will find mg square H square equals F square H parentheses 2L minus H. So if H is non-zero, so H can be zero, of course, that's one solution, that's at the bottom. And if H is non-zero, we can cancel one of these H's, and then we will find that m square g square H equals to 2f square L minus f square H. So I can put this in H parentheses. In H parentheses, I have m square g square plus f square is equal to 2f square L. So my answer for H as a function of f is, if I divide both sides by f squared, this will be equal to 2L divided by 1 plus mg over f square. Why did I do this, divide both sides by f square? Because I want to get my answer looking dimensionally correct. So this is a length, this is a length. Here is a ratio of two forces which is dimensionless. So dimension of H is equal to dimension of a length which is correct. So this checks in terms of physical dimensions. Now we're going to substitute some values for the force. So if I put F equals 1 newtons, this will give me for H, and I have to be careful with SI units here, 80 centimeters is 0.8 meters, 1 plus divided by 1 plus, it was 300 grams, which is 0.3 kilograms, 9.8 meters per second square, divided by 1 newton, 1 square, and that gives me 0.166 meters for H. Now I try 10 newtons in part C. If I put F is equal to 10 newtons, what is the maximum height I can reach? This time it will be 2 times 0.8 divided by 1 plus 0.3 times 9.8 divided by 10 parentheses square, which is 1.47 meters. And in part D, I try F is equal to 0. F is equal to 0 newtons gives me, for this solution also, 1 over, so if I substitute F equals 0, I will have 1 plus 0.3 times 9.8 over 0 squared, so that will be 1 over infinite. So this is going to become 0 meters as the solution. So with no force, it should stay at the bottom. If the force is infinite, what will happen to the maximum height? If f goes to infinity, h becomes 2L divided by 1 plus 0. 1 over infinity is 0. So this is going to be 2L. So that is 1.6 meters. Does that make sense? So if I apply an infinite force here, the maximum height I can reach here will be equal to 2L. So I'm going to reach the top, basically. Okay. And part F. Now I have the equilibrium situation. So let's look at the equilibrium free body diagram. So I have mg pointing down. The constant horizontal force F to the right, and there will be a tension making an equilibrium angle with the vertical. So let's call this a y-axis. This is our x-axis. The net force on the x-axis must be 0, which means T F minus T sine theta equilibrium should be equal to 0. So T sine theta equilibrium must be equal to F. And the net force on y should be 0, which means T cosine theta equilibrium minus mg equals 0, or T cosine theta equilibrium is mg. So I want to divide these two equations to find tangent theta equilibrium. Tangent theta equilibrium is F divided by mg. So if I draw a right triangle here, this is F, this is mg, here is the theta equilibrium, and this is square root hypotenuse f square plus mg parenthesis square. I find that cosine theta equilibrium is equal to mg divided by square root of f square plus mg square. So the equilibrium value of h will be L minus L cosine theta equilibrium. If you remember from this geometry, if this is theta equilibrium, then it will be L minus L cosine theta equilibrium, which will be equal to L times 1 minus cosine theta equilibrium. Okay, so we can plug in this result here into this equation to find the equilibrium value of H in terms of F. We find H equilibrium is L times 1 minus mg, it was cosine theta equilibrium, mg divided by square root f square plus mg parentheses square, which is L times 1 minus, now I'm going to divide top and bottom with mg, 1 over square root 1 plus f over mg square. Again, I do this to get the dimensional picture here. It has the dimension of L length. Now part G says substitute F equals 10 newtons for this equilibrium height. If F is equal to 10 newtons, H equilibrium will be length 0.8 times 1 minus 1 over square root 1 plus 10 over 0.3 times 9.8 parentheses squared, which is going to give us 0.574 meters. And if we have f go to infinity, where will I have equilibrium? The equilibrium height will be L times 1 minus 1 over infinite, which is L. So this is going to be L, which is 0.8 meters. Okay, so to summarize, we have a ball of mass m that is at rest at the bottom, and it's under the influence of a constant horizontal force F. It goes to a maximum height and then it swings back. We want to know the maximum height as a function of F and the equilibrium height as a function of F. So to do that, first we have looked at the geometry and found that there is a relationship between the length of the string and height, the maximum height or the equilibrium height we reach. If the string makes an angle of theta with the vertical, it is L minus L cosine theta. From the cosine theta becoming L minus h over L, we have determined also sine theta. Because we have a constant external force being applied that changes the mechanical energy of the system, delta U plus delta K is the work done by the external force. This allows us to find H as 2L over 1 plus mg over F parentheses squared. And we have evaluated it for 1 newtons and 10 newtons. We see that it's approaching 2L as F goes to infinity, and it's approaching 0 as F goes to 0. For the equilibrium angle theta, we can do the same exercise by noting that the net force on X and net force on Y should be 0 at equilibrium. And this allows us to find H equilibrium in terms of F. And we have evaluated for F equals 10 newtons. Now, instead of having this 1.47 value, which was for maximum height, equilibrium height is 0.574 meters. And the equilibrium height as F goes to infinity becomes L. So that makes sense. If you apply a basically infinite force F here to the right, this will be at equilibrium position, pointing in the horizontal direction. Okay, let's move on to our last example. A uniform chain of length 8 meters initially lies stretched out on a horizontal table. Assuming the coefficient of static friction between the chain and the table is 0.6, show that the chain will begin to slide off the table if at least 3 meters of it hangs over the edge of the table, and determine the speed of the chain as its last link leaves the table, given that the coefficient of kinetic friction between the chain and the table is 0.4. Now you can see that this was initially stretched out, now it's hanging over the edge, and let's call the fraction that is hanging F. So L times F length is hanging, L times 1 minus F length is still on the table. So a fraction of the length F hangs from the edge and this is a uniform chain. The meaning of having a uniform is basically a uniform distribution of mass. The total mass divided by length is the mass density. So the mass that's hanging over the edge, we can find to be the mass density m over L multiplied by the length F times L. So L's will cancel, so it is mF. And so we find that the hanging weight will be mFg. Now the part that is remaining on the table, we can note the remaining part on the table has mass m times 1 minus f and weight mg 1 minus f, which is going to be balanced by the normal force, because this portion is not moving on the vertical axis. The normal force on the table I'm going to call N. So there will be a normal force here, N, which is acting on the portion that is still on the table. Okay, now we want to show that the chain will begin to slide off if at least 3 meters hangs over the edge, which means we have reached the maximum static friction. The maximum static friction will be equal to the coefficient of static friction times the normal force. The coefficient of static friction was 0.6. The normal force is mg 1 minus f, because it's balancing the weight that is on the table, and this must be equal, so this force must be equal to the weight of the portion that is hanging, mgf. So if I draw a free body diagram for the hanging portion, I will see that it's going to feel the weight mgf, and there will be the friction force, static friction, which is balancing it if it's not sliding. If it's at the verge of sliding, that the static friction has reached its maximum value, so these m's will cancel and I will find 0.6 m's and g's will cancel. 0.6 minus 0.6 f must be equal to f, which means 1.6 f is 0.6, or f equals 3 over 8. So the length that is hanging over the edge should be equal to L times F. It was 8 meters in total. 3 over 8 is the fraction that is hanging, so it is 3 meters. Now let's move on to part B. Now the sliding has started, so let's note that after the sliding starts, the hanging weight will become mg times, because there's an extra portion that has moved down, 3 plus x divided by 8. So as it moves down, a distance x. And on the table, we have again mg. Now we have 3 meters, 8 minus 3, 5, 5 minus x divided by 8 as the fraction that is remaining on the table. So this is remaining weight which is going to be balanced by N. So the kinetic friction force, which is mu k times N, will become 0.4 times mg over 8 times 5 minus x. Okay, so let's take a look at the free body diagram for the hanging portion again. It's going to be mg 3 plus x over 8, which is counteracted by kinetic friction, and it's moving down. So the net force on the y-axis is basically mg 3 plus x over 8 minus the kinetic friction, which is 0.4 over 8 gives us 20 mg over 20 5 minus x. This is our net force acting on the x direction, and this x will go from 0 to 5 meters, so that when its last link is leaving, we're going to have all of this hanging over the edge. So it will become 8 over 8, the fraction will become 1, the whole thing will be sliding over the edge. So the net work done, or the work done by the net force, is the change in the kinetic energy of the system, work kinetic energy theorem. The final velocity will be v, let's call, so we will have 1 over 2 mv square as our final kinetic energy of the chain, and this will be equal to the work done by the net force from 0 to 5, the net force dot product with displacement integral. So the change in kinetic energy, 1 over 2 mv square, is the integral from 0 to 5. Then I will have for the net force mg 3 plus x over 8. So let's have a common denominator. So this will make this 2.5 mg 3 plus x minus mg 5 minus x divided by 20, common denominator, dx. So I multiplied mg over 8 by 2.5, top and bottom, and this becomes integral from 0 to 5, 7.5 mg plus 2.5 mgx minus 5 mg plus mgx divided by 20 dx. So this will give me 1 over 2 mv square equals integral from 0 to 5. 7.5 mg minus 5 mg will give me 2.5 mg, and 2.5 mgx plus mgx gives me 3.5 mgx divided by 20 dx. This will become 2.5 over 20 mgx as I integrate it, and this will become 3.5 over 40 mgx square. 1 over 2x square is the integral of x. This whole thing will be evaluated between x equals 0 and 5. So that will give me, if I get rid of the masses here as well, This will give me 2.5 times 5 over 20 plus 3.5 times 25 over 40 g for v squared over 2. So I will find that v will be square root 2g 12.5 over 20 plus 875 over 40, and the final speed is 7.42 meters per second. Okay, so I used if I calculate the net force acting on the system, work done by the net force is change in kinetic energy. So I use this work kinetic energy theorem in order to calculate the final speed of the chain as its last link leaves the table. And first I have noted that I have kinetic friction now, and there is an extra part x that's hanging and 5 minus x remaining on the table in order to calculate this net force. And by calculating the work done by the net force, where x goes from 0 to 5. X equals 0 is when we start sliding, x equals 5 is when the last link leaves the table. This integral gives me the change in kinetic energy 1/2 mv squared minus 0 by 0, because the initial kinetic energy was 0. We just started sliding, and this gives me the final speed as 7.42 meters per second. Now you can also note that when I look at the change in mechanical energy of the system, delta K plus delta U, this should be equal to minus integral Fk dx, because the friction is a non-conservative force. It causes a decrease in the mechanical energy of the system. So what I have done here using work kinetic energy theorem, you can show to be equivalent to this statement. Basically, the work done, there is no work done by a non-conservative force. All it does is decrease the mechanical energy of the system and convert it to heat.